Hello, this is stat134, lecture 1. Today I gave an announcement, we did an icebreaker, and then we started in the book sections 1.1 on equally likely outcomes, 1.2 on interpretations, and we started section 1.3 on distributions. So there was no lab today, or there was a lab today. Also, pre-lecture notes are on B courses pages, so make sure you check that out before every class. Last year I had people downloading them onto their iPad and then just writing and filling in the notes. The website, as you know, is stat134.org. The schedule is up. My office hours are before class in the SLC. The adjunct class with Mike started yesterday. Contact him for more information. I thought I would share with you some student comments. The one I really want to emphasize is to go to every section and lecture. Doing that gives you an immediate advantage over half the class. So the point here is that even though I'm providing these videos and the on-class notes, you really get a lot. You get a lot out of attending class, so you really don't want to get complacent. So then we did an icebreaker, and so I asked you which of the following pictures describes probability and which describes statistics. So we agreed that the bottom one is probability. In probability, for example, you have a pail of different colors and you reach in the pail, you're taking a sample from your population, and you can tell, for example, you can answer using probability a question such as, what's the chance that I get at least one of each color? In the top picture, we're doing the reverse process. Statistics is in fact inverse probability, where we know what's in our hand. We know we've taken a sample from some population. We don't know what the distribution is of that population, and that's what inferential statistics is all about. So then we started section 1.1. So we have omega is an outcome space and also called a sample space. So for example, if you have 3 cards, Jack, Queen, King, you would have 6 different orderings of those 3 cards. That would be our outcome space. And let A be the event that the second card is a queen. So there's 2 ways that can occur. So you can ask, what's the probability that the second card is a queen? Because all the outcomes are equally likely, the probability of A is the number of ways A can occur over the total number of possibilities. So that turns out to be a third. Remember that a deck of cards has 4 suits. Each suit has 13 ranks, so we have a total of 52 cards. We then did a problem. Suppose a deck of cards is shuffled and the top 2 cards are dealt. What's the chance that you get at least one ace among the 2 cards? A bunch of you did this differently. One way is just to think of what A and omega is. So omega is all pairs that you can have. We're drawing these cards without replacement, so we have 52 times 51 possible pairs, and the occurrences of at least one ace. We could have 2 aces, 1 ace, and a non-ace, or a non-ace and an ace, and we can count the number of ways those occur, which, for example, for ace-ace, you can visualize as using a tree diagram that there are 12 possibilities. Another way to do this was to recognize that you can find the complement of A, which is that you get no aces, and then what we're looking for, the probability of at least one ace is 1 minus the probability that there are no aces, and the probability that there are no aces would be 48 times 47 over 52 times 51, because there are 48 non-aces to choose from for the first draw, and then 47 for the second draw. in both ways you get the same answer. We then did a slightly trickier problem. 2 draws are made at random with replacement from a box with 10 tickets numbered 1 to 10. Find the chance that the second number is bigger than twice the first. So again, omega here is all pairs of numbers, so there's 10 times 10. And A, we can just think of all the ways that we could have a pair. So for example, if we choose a 1, then the second has to be larger than 2, and there's 8 ways to do that. If you choose a 2, then there's 4 ways. Then the second has to be larger than 4, and there's 6 ways to do that, etc. So A, the size of A is in fact 20, and we get 0.2 for the probability. So probabilities have 2 interpretations. There's a frequency and a subjective or Bayesian interpretation. The frequency interpretation is where essentially you do an experiment and you see what you get, and you can we have the law of averages, which says that if you do this experiment repeatedly, that the average of the probabilities that you get are going to be the true probability. So for example, say that I have a fair coin, my experiment is that I toss it 100 times and count the number of heads. So you're not going to get 50 heads every time, right? You're going to get 49, then you're going to get 52, and so on. So you're going to so the probability of getting heads in each experiment is fluctuating around 0.5, and on average it will be 0.5. That's the law of averages, and you can read about that in the book. The subjective interpretation occurs in situations where you can't really make an experiment that is repeatable. In this case, probability is based on an opinion. So for example, the probability that a particular patient survives an operation is not something that you can test over and over again because it's a particular patient. But your opinion can change over time based on information that you learn about the patient. So for example, if the patient has some complications or is in excellent health, those will change your opinions about whether the individual will survive. So in section 1.3 we get into the nitty-gritty. So again, outcome space is omega. We assign to every element a non-negative, so every element in the outcome space a non-negative number, and require that all the numbers add up to 1. So we have 3 axioms. So for every subset of omega, the probability that every subset A of omega, the probability that A is greater than the probability of A has to be a positive, a non-negative number. You can think of omega as some box or some square with total area 1, and A is a collection of elements in the set. Let's just denote it as this circle here, and the probability of A we can think of as the area of that circle. We can think of the probability of omega as being 1, and that's in fact the second axiom. The third axiom is the addition rule. If A and B are mutually exclusive sets, which means that they're disjoint, then the probability of A union B is the sum of the probabilities. So the probability of A union B will be just the sum of these areas. Just is totally intuitive because that's just the way areas add up when they're disjoint. Okay, so here we'll do an example. So we have this die of variable width. The width is t, and so this thickness is such that the chance of landing flat is flat, meaning 1 or 6, is 2/3. So we want to find the probability, the distribution. We want to find the probability distribution of this shape, and we also want to make a histogram. So to do this, we need to figure out. We know that the probability of 1 and 6 are the same just from the geometry. So the probability for the other 4 sides are all going to be the same. We have to figure out what that is. So we just write a simple algebraic equation and figure out that it's 1/12, and then we can just make our histogram as shown. So the difference rule. So suppose that B is a subset of A. So what I want to find is the probability that that I have A not B. So that's the difference. It's also A intersection the complement of B. In other words, you're in A and you're not in B. So A/B or A/B complement both mean the same thing. It's this annulus region here, A that's not B. So we want to find a formula for this difference using our axioms. The trick here is to write A as a disjoint union. We can write A as B union the difference of A and B. And then we can just use our addition rule. And then we can just do algebra to write the probability of A minus B is probability of A minus the probability of B. So it's probably kind of obvious that the probability is probability of A minus probability of B, but the point is that it's something that you can derive from the axioms. The complement rule is the probability that the complement of B is 1 minus the probability of B. And to prove this, the key here is to use the difference rule and to realize that you want A here to be the entire outcome space. So then the complement of B is omega minus B, and then we have the probability of the complement of B is probability of omega minus probability of B. In other words, 1 minus probability of B. Finally, we did the inclusion-exclusion rule. The inclusion-exclusion rule is very important. So it says that the probability of A union B is probability of A plus the probability of B minus probability of the intersection. The main idea here is that the intersection is double counted here. It's included when you're computing the probability of A and the probability of B, so you need to subtract it out. But we can prove this from our axioms. The key idea here is to write A union B as the disjoint union of A and B minus AB. And that just then, by the addition rule, is probability of A plus probability of B minus AB. And we know what the probability of B minus AB is from the difference rule, and that gives us what we want. So we will pick this up next time. Have a great night.